Hello, everybody, and welcome to the QTEdu Demo Day of Educational Tools. Today, we are glad to have with us Zohaib Khan from Kwanteach company, and he will be presenting their experimental platform for teaching quantum physics. Zohaib, you are welcome, and the stage is yours.
Thank you very much, Oksana. Hello, everyone. So my name is Web Khan. I'm the sales manager for Kwanteach, and we gather here today so I can share with you and show you how our experimental platform, the Kwanteach, can really modernize your quantum physics teaching. So I'm gonna, before going directly to the setup, let's just present who we are. So we are Kwanteach. We're a French company specialized in quantum sensing solution based on NV centers in Diamond. So we are located in the west of France, in Brittany, and we have been founded after 15 years of experience in teaching and research in quantum science. So our core expertise is the Diamond quantum sensors. So what we are here today.
Zohaib, your
Yes.
video is not showing for some strange reason.
I'm sorry.
Your video is not showing you.
Oh, so you cannot see me right now.
Oh, yes.
Okay. And so what we are here together today is, as you may know, today quantum technology training is a global need. So we have been experiencing a lot of advancement in the quantum technology fields, in computation, algorithm, in computing, sensing, metrology, and communication. But it's necessary to have the trained workforce and develop the background of the future generation of quantum engineers and quantum physicists. And this is why we think at Kwanteach that the practical training has been a real major innovation that we have to work on. So this practical training has been outlined by professors in all kind of universities and institutions, and we will show today how you can address this topic, the practical training, alongside you with your classics theoretical lectures, and everything with the Kwanteach, our only all-in-one open platform for quantum physics teaching. So in the next 20 minutes of today's session, I will show you and briefly remind some theory about the quantum and the quantum diamond sensors and the NV centers of diamond. Of course, this is not a real physics lecture, it's just a reminder. I think all of you know mostly. Then I will describe how we are addressing these issues with the Kwanteach, and the last step would be to show you live demonstration with our setup and the software. So as I said, the Kwanteach's core technology is the NV centers in diamond, where we will be using a specific kind of diamond where one of the carbon atoms will be replaced by the nitrogen atom near an atomic vacancy. This creates the NV center in diamond. So by shining with the green laser, we will be detecting the red fluorescence. And this specific defect has an exceptional optical and quantum properties that will allow us to have a precise measurements of various quantities. It can be magnetic field, temperature, or other, but in our case, we will be focusing on magnetic field sensing. But how does it work? Basically, the NV in diamond is a quantum system with three states. It's with an electric spin of s equal 1. So you have three states, the ms equals 0 state, ms plus or minus 1 state. The ms equals 0 state is the bright state, and the ms plus and minus 1 states are the dark state, means that they emit less light. So what we will be doing, we will be shining a green laser onto the diamond and measure the fluorescence out of the diamond. And there are two key properties about the diamond, is that when it's under emission of a green light, all of the electrons or most of the electrons will be polarized in the ms equals 0 state. Then we will have a maximum of fluorescence, that we call the bright state. And now, if you apply the right microwave frequency, you will be able to see the transition between the ms equals 0 state to the ms plus and minus 1 state. And due to this very specific frequency of 2.87, you are able to see that you will experience a drop of fluorescence level directly on your curve. And then you can see that your electrons have actually changed states. And this is what we are doing. So basically, what you have just done right now is you have optically detected the magnetic resonance. And that will be one of the first measurement that we will be doing with our setup. So as you can see on the picture on the right below, you have a maximum of fluorescence. And now, since you have the transition between the ms equals 0 state to the ms plus or minus 1, you have a drop of fluorescence. And what we will be doing, we will make a frequency span for a low frequency to a high frequency to be able to detect this. But you can actually use the NV as a magnetic field sensor. But how do you detect actually a magnetic field? So in the presence of a magnetic field, your ms plus or minus 1 state will be actually splitted proportionally to the norm of the magnetic field applied. So in the diamond, you have plenty of NV centers, and they have an orientation. And depending on the orientation of the magnetic field, you will be able to see different kind of configuration and different kind of lines. But according to the norm of the magnetic field, your splitting between the ms plus 1 and the ms minus 1 state will be bigger or smaller. So this is exactly how you are able to measure a magnetic field. By measuring the difference in frequency between those two states, you are actually able to find, to retrieve the magnetic field. And this is how we will be using it in our case, but this is how we use it also in more industrial application where we are doing quantum metrology. So the NV center is a vectorial, absolute, sensitive, and small magnetometer. And to explain you a little bit and how we can apply this to our future generation of physicists, we have developed the Kwanteach. That is a fully open and modular platform using optics, various basic optics, in order to highlight those quantum properties. We offer a wide range of experiments, up to 15, with everything provided. And we provide then the hardware, the software that you can see it, and also the units that have been specifically designed to control the whole setup. As you can see, the setup is fully open and customizable to fit as best your needs. So we have already 1,000 hours of use, and the system is really reliable right now. So I think let's switch to the setup. So I'm gonna show you right here the last slide. Of course, as I said, we provide 15 different experiments, and we also give you the full technical manual. Okay, so let's start with, I'm gonna just share my screen so you can see the setup here. So you should be able to see here the setup. So we have very first here, we have a green laser that is going through a couple of optics here, through a dichroic, and we will shine into the 3-axis Helmholtz coils. We will be focusing the laser on directly the diamond. So if I could see here, you can see that the diamond is actually put on a PCB. That would be the RF and the microwave antenna. And if I apply, for example, just a red filter here, you are able to see that we actually focus our laser onto the diamond. So you can see here, this is the antenna, and this is the diamond that is glued onto the antenna. After that, once you have focused the laser onto the diamond, then you can follow here the path to the dichroic, then the lens to focus the laser and the fluorescence onto the photodetector. And you should be able to see maybe here on the white paper. I'm going to try to show you a white paper here. And if you really focus a little bit here, you're able to see here the red fluorescence directly onto the detector. So that's a very, very easy to see and very didactic, I would say, didactic tool for students to see what they can do. So this is the very basic software. So this is what we call the base module. Of course, we have a pulse module that I will show you afterwards. And before going to the pulse module, I suggest we just go through the software. So I'm going to share my screen again. You should be able to see my screen right now. And so that's the stop sharing. Yes. And now, sorry. Now you should be able to see the base module. So you should be able to see my screen right now. Okay. So now if you look at the screen right now, you can see that we have a GUI that is pretty simple. You have one box for acquisition settings where you can set the low frequency and the high frequency for the span. You can change the number of averages, the number of points, and also the hour power, that is the microwave power. That is very interesting because you can see the impact of having a high power microwave or a low power. Then you have a small box when you can generate the magnetic field. So this is what we do with the coils. We generate the magnetic fields. You have two options. Either you use the spherical one with the norm, the theta angle, and the phi angle, or you use the Cartesian way. And you have finally the graphical representation. So let's start really easy and quickly. So let's put 2.7 gigahertz for low frequency and 3.1 for the higher frequency. And you are able to see now, we just have to click on start and you are able to see directly an ODMR that will be drawing itself. So just by a simple click, you are able to see here the ODMR. That is the optically detected magnetic resonance. You can see here at 2.87 gigahertz, you have this drop of fluorescence. And you are able to see at this location frequency that all your electrons have actually made the transition. But we can go a little further. And if you want to see the Z-man effect, that is the splitting of your MS plus or minus one state that you can see on the left side and right side of the 2.87. So we will be just focusing our grid here onto this center around this part. So I'll just pick 2.78 and let's say 2.96 just to be sure that it's centered. And we will apply a magnetic field. So I have set the magnetic field. I'm just going to use the 1.9, I would say a small magnetic field with the 32-degree angle for theta and the 23-degree angle for phi. You just have to click field on and you can click start. So now we should be able to see this splitting of the line. So if I'm just going to rescale a little bit and start again. And now directly on here, you are able to see that you have multiple families. So we are in a configuration where the magnetic field is not aligned with one of the axes of the NV inside the diamond. So you have some NVs seeing one magnetic field and some others seeing another magnetic field. So this is how you can definitely see it. So you can change different configuration here to have different values here. But let's focus on the 2.87 here on those two lines. Another point is that you are able to see here on the left side, for example, three little drops that correspond actually to the hyperfine structures inside the diamond. So that is also something very interesting for your students to see directly in live with simple setup. So if we that now just increase the magnetic field applied, so if we follow the Zeeman effect, we should be able to see higher splitting between those lines. And now you just have to click on and clocks to try to click start again. And now we will be able to see around the 2.87 gigahertz that we have a splitting on the lines, meaning that due to the increased magnetic field, those lines -1 and +1 ms -1 and ms +1 are actually splitted. So this is something very easy to say. Of course, you can do a lot of different experiments. You can do the magnetic field, the Earth magnetic field measurement. You can have a noise analysis tool. You have a lot of different tools inside the setup. But I will just briefly would like to show you the pulse version. So if I change again, just going to click share here, and we can switch again to the black magic, and then you can see here. Oh, here, can you turn on the light, please? Thank you. And now here, if we would like to go from the base module to the pulse module, you just have to flip here 1, 2, and 3 mirrors. So with the same setup, you are able to have a simple switch between base module and pulse module. So if we just go through the optical path, we are using the same laser. And here we are sending the beam through an AOM, that is an acoustic modulator, in order to generate pulses of laser. But we will also, with the units that we have designed, generate pulses of microwave. And then with the other optical element, we will combine the pulse path with the base path that you have seen before to the same coils, and the microwave antenna with the diamond to a second photodetector here that is fiber coupled, in order to make sure that we are seeing everything needed. So if now I would like to show you just one of the very basic measurement that we can do on the pulse module that are the Rabi oscillations. So if I share my screen now and go to here, and I can show you the pulse module here. You should be able to see this pulse module, okay? And now you can see that on the pulse module, we have different kind of experiment, for different tabs. So you have the T1, the Rabi oscillation, the Ramsey fringes, the Han echo. And let's focus on the Rabi oscillations quickly.
We see the same board that you showed before for measuring the
okay. So let me
presence.
just correct this. So you should be able to see the share, and I'm going to share the entire screen. It's easier. And now, up. And now you have that, right? Great. So you should be able to see the T1, Rabi, Ramsey, Han echo tab. And you have on the left side, and for each pulse module, each pulse measurements, we have a sequencer, and this will be able to generate sequence and change the sequence as we wish. And before doing that, let's say we would like to make, for example, Rabi oscillation around a specific ODMR measurement. So we just have to go inside the base, choose one of the hyperfine structure here frequency. So let's say with the cursor, we can find either this one or maybe this one. That is probably easier. And you can see that it's 2.79120. We just have to change inside the sequencer of the Rabi, that is here, we just have to change the number. So it's 2.79120, and I'm just going to 2.79120, and then we have preset everything with my colleague here, and then we are changing the sequence, and then you can see here directly the sequence where we switch from microwave to laser to other to a certain dead time. So this is what we will be doing. So we will increase the laser pulse, just set sequence, and go in the pulse module, and on the T1, you can click start just to see. Okay, so now Paul is going to, my colleague is actually going to, I would say, adjust the pulse, so it's going to be easier for you to say. So he will be adjusting the pulse for each measurement. So for the pulse module, you will have a very fixed setup and fixed configuration where you can perform all your measurements in the pulse module. So the T1, that is the relaxation time, or the Rabi oscillations, or the Ramsey fringes. So we are using, for example, in this case, the T1 measurement as a reference, and you can see that he's actually changing. I don't know if you can see it, but we are changing and then adjusting the focus. We are adjusting the position of the lenses, etc. And here, what you can see also is that once you have set and click start, on the left side of the screen, you can see the pulse for each pulse. And on the right side, you have the result of the measurement. So on the left side, you are able to see each pulse that we're sending in the sequence. And on the right side, each points that we have done for our measurement. So in here, we are measuring the T1. But if we would like to go to the Rabi oscillations, when we have set it, we just have to go on the sequencer, set the sequence, and click start. And now we will be launching a Rabi sequence where we will be, and the Rabi sequence, for as a reminder, is a measurement that describe how the state of this quantum system, that is the NV, are populated. So we will make the transition between the MS equals 0 to the MS plus and minus 1 state, back and forth, and we should be able to see, if the world would be perfect, we should be able to see a perfect sinus. But due to decoherence, and this is what the Rabi oscillation provides the information, we could see a decreasing oscillation in sinus. And this is exactly what you are able to see on the right side. You have a maximum of signal. So you have the maximum, all your electrons are located in the MS equals 0 state, for example. And then after a certain amount of time that we call it the pi pulse, you have most of or all of your electrons that are in the MS plus or minus 1 state. And then by doing this back and forth, we are able to see an oscillation in the population of your quantum states. So, and this works at room temperature. So at the room temperature, you are able to show and highlights quantum principles that usually requires cryogenics, that usually require vacuum or big instrumentation. But in this case, really easily in just a couple of clicks, you are able to show and highlight very deep quantum principles that are used in quantum sensing, of course, but also quantum computation, quantum communication, and quantum computing in general. So this gives an idea on the decoherence and the spin manipulation, and everything is all in one single setup. So this is, I think, the end of my presentation. You are able, of course, we have added the fit if you would like to see how does it look with the R square factor and the pi pulse. So we have the pi pulse that is here, which said to us that all of the electrons are in the MS plus or minus 1 state. There have been the inversion of population, and the pi over 2 pulse in here, this means that we have a superposition and a linear combination of the two states. ms equals 0, and then plus or minus 1. And then you can stop, of course, whenever you want, and have directly the curve that is saved onto your computer and with all data. So we provide, of course, the raw data, so you can have access if you would like to make some post-processing work for your students or for yourself, and then you can also add them in your own code if needed. So I think on my side, it's pretty okay. Do you have, I think we can stop here for our side. I hope I haven't been too long, Oksana. So we can switch to the question if you have some. Be glad to have.
Absolutely. Thank you so much, Dohaib. That was a very punctual presentation. Yes, you are
Thank you.
perfectly in time.
Great.
And now we have easily a lot of time for questions and comments to the presentation.
Sure.
And you're welcome to write them in the chat or just raise your hand or and speak up, because we are very few people today and we can comfortably ask questions live.
Yeah.
And meanwhile the questions are coming up, I would like to ask you about your experience with this setup in the classrooms, and what are the challenges that the teachers experience with your setup, and what are the solutions they usually find.
Yeah. So our setup is firstly used for bachelor students. Master students can be used for doctoral students as well. So really depending on which kind of configuration, you will face different kind of challenges. All challenges are able to find a solution. So this is why we are here. But for example, the base module can be adapted for bachelor students to have a first insight of what is quantum technology. The pulse module can be really interesting for students in applied physics, quantum technologies, nanotechnologies as well, where you can really have a deeper knowledge of atomic and molecular optics, or quantum technology and nanotechnology as well. And the thing is that depending on which configuration you are, the content of your lecture would be different. But the good thing is that with the platform, since it is totally open and modular, it can fit and adapt to every single lectures. And we, on purpose, leave the stage to the customer to change the platform as they wish, in order to have a better use of the kit.
Okay.
Right now we have I would say more than 1,000 hours of use on the system in France and worldwide. And the feedbacks are just great, because it also helps us to, for each new system order we have, we keep that into account and we change accordingly to make even robust, more reliable system day by day.
Mhm. Very nice. And how long is usually one? How much time do students need to complete one experiment?
So again, it depends on the experiment. For example, as you can see on the ODMR, we have done it in like just 2 minutes on the software. However, to perform a real ODMR and complete, you also have to perform the optical alignment, the noise analysis, and depending on the level, so it's bachelor, master, or doctoral, the lab courses duration is different. Sometimes it's 4 hours, sometimes it can be 8 hours, and it can be also used in projects. So basically, if everything is well aligned, um, the measurements don't take too much time. But one of the greatest thing here is to align the system and make the noise analysis, the noise budget analysis, and optimizing the signal to noise ratio. So really to have a full hands-on the imaging and also the measurement chain is really important to have the full. So usually in 4 to 8 hours, students are able to have and perform all of the experiments.
Okay, so you mean that the most time they spend for preparing the system and then the actual measurements go really smooth.
Yeah, it's really on the software, but preparing, measuring, and understanding what you are doing. This is also why we all have let the system open so they can really have a hands-on. It's really important to us, and that can be depending on the level of your audience, can be longer or smaller. But we have especially dedicated with classic mirrors and optics, so they have a simpler way to align it without too much trouble.
Right. Okay, and maybe you could share with us also how expensive is your platform?
So we have actually multiple offers. You can have also only the base module. As I show you can have the base module plus the pulse module, and depending on, I would say, the option you go with, the price will be different. So we try to keep it as much as possible reasonable for education and lab courses. But for any, I would say, business related question, you can just contact me, drop me a mail, and I will be happy to show you all our options. We also have rental offers for people that would like to test it for a few months, for example, before secure it, or for highlighting it during summer school or winter school or specific events.
And the order of magnitude of the cost for the rental?
That would also depend on the duration of the rental. So we are trying to, I don't know, we really go as best as we can to don't be too expensive. But for any business related question, please drop me a mail. That would be the most easy way.
You said that your modules were used also for teaching to the doctoral
Yes.
students.
Yeah.
And
It can be, yes.
but in case you already have feedback from that experience, could you please share with us how was it used in particular?
So right now we have developed the platform in an open way. So even for young doctoral students, they can have, I would say, a training on the quantum sensing metrology using the platform, but of course not directly into the research. And we are actually talking with some partners in Europe that could be interested by implementing it in a doctoral path. But right now we are mostly working with master's level and bachelor levels.
I see.
And the good thing is that it can be adapted because as I said, it's an evolutive way. So you can also, for example, think about an evolution where you can change the sample. So you can have a diamond with more or less concentration of NVs, or have a different samples. All of these evolutions are possible. We are thinking about it also, and this could be proposed for students in NV, for example, or PhDs in NV or in quantum sensing in general, magnetometry, and things like this.
Mhm. As we have mentioned quantum sensors a few times, and the Kwanteach is a company which is producing quantum sensors. Could you share with us what area of applications,
Sure.
what is the main area of applications of the sensors produced by Kwanteach?
Sure. So we are of course actively working in the education part with the Kwanteach, but our core technologies are quantum sensor for industrial application, and we have, for example, for now working on the non-destructive testing, where you are able to detect some defects by measuring very locally the magnetic field changes with the diamond. And another thing would be to um, use the diamond as a quantum sensor for navigation. So this has multiple use in drones, in navigation in the sea, or other application where you need to navigate without relying on GPS, for example. So these two are the most, I would say, um, interesting field we are working on right now with our industrial quantum sensors.
Very nice. That has been a very insightful and
Thank you.
great presentation. Zohaib, thank you very much.
Thank you.
Unless Piotr, that is with us, have other questions to you, I think we can already move to the conclusion.
Sure.
No, thank you. It was really interesting presentation. Apologies, I was a little bit late, but really interesting presentation, and thank you for the thank you for the overview.
Thank you very much.
Piotr, I could share with you the link to the to all the videos that we record of the training, because we collect them on the YouTube channel of Quantum Flagship, and there is a specifically dedicated playlist where you can find them all demo days.
Yes, exactly. Thank you, Oksana. I'm also a part of the research and networking community within JAD, and we also have a kind of academy, and we try to align with QTEdu, also the flagship activities, with some training and education material there, also using the training platform and also InfoShare. So I try to connect a little bit those two activities.
Very nice. Okay. Great. Then, thank you so
Thank you very
much,
much.
Vibe, one more
Thank you very
time.
much, Oksana and Piotr.
Thanks.
And looking forward for other occasions to meet.
Sure.